Okay, so this is really just, making the various parts explicit again. And so what people did before us is essentially the following. They said, well, let's just take our data set and split it up into, maybe give 1,000 machines, 1,000 subblocks. And for each subblock, let's pretend that all the other machines didn't do anything, and we just sampled that subblock. And in the end, you have a merge phase, where you merge all those observations together, and then you will go and update again. And this can be done reasonably efficiently in MapReduce, because basically the mappers would just correspond to one of those sampling passes, and then the reducer would actually merge all the updates. Mind you, you'd essentially be destroying and creating the same data structure over and over and over again, which is a ridiculous waste of time. But the bigger issue is if we look at those three terms here, right? Then, well, what it actually tells us is that this, decomposition is more or less efficient. If you look at the first term here, the only part that really depends on all the other machines is the number of times a particular topic occurs. Now, if we have, hundreds of millions of documents, this changes very, very slowly. So, just sampling, one document or something isn't going to change that number a lot. So that's essentially constant. So we don't have to worry much about it. It's very slowly changing. Now this is rapidly changing. That's the number of times a particular topic occurs in a particular document. But that sits within a single machine anyway. So that's good. So we don't have to worry about that either. So this is good because it's so slow. This is good because it's machine local. Now the thing that actually gives us a big headache is this term here. Is that's the number of times a particular topic occurs for a particular word. And while the total number of occurrences for a particular topic might be, millions or billions, this could very well be, in the tens. So what we need to worry about is how do we keep that part of our state synchronized between machines. Now if we go and, if effectively, wait until we are through an entire block, it means that these tables really go out of sync. And it's very memory inefficient because we basically have to keep that full table around for each machine. If I have multi-core, they might actually do that for each core separately. And it's a blocking procedure because it means you have to wait until everybody's done with its pass, and then you synchronize and then you can move on. It also means that the algorithm becomes heavily network bound. So how do we fix that? In hindsight, it's actually super simple, right? So what we do is we just run a synchronization thread in the background that keeps things synchronized within a machine for multi-core and between machines by essentially using this distributed hash table that we did in lecture number 1. And don't worry, we'll get through that and we'll go through it in detail again. But there's a reason why we did all the system stuff in lecture number 1. Coming back to bite us now. And then, basically all the good things happen that, you're basically using all the resources, you only see the variables that you really care about, you continuously sync, and, well, basically, there's no barrier that you need to hit. And not having a barrier is good because it basically means that all the slow machines, occasionally some machines go wonky, they have time to catch up. So, let me explain what it really means in terms of implementation on a single machine. And this is essentially the fastest multi-core LDA code you can find that uses sampling. Okay. So what it does is, so this is implemented using the Intel threading building blocks, which is a very nice parallelization library if you ever need to parallelize stuff in C++. So Java has its own functionality that has all those pipelines and so on already built in. So in Java you wouldn't have to worry about it, but if you use C++, I can strongly recommend this. basically we have a pipeline. And each stage in the pipeline we have filters. Some of those filters can be invoked in parallel. Some are, of some we only have a single one. Okay. So first of all we need to read data from file. So what we actually do is we store the documents and the topic assignments in two separate files. The reason for doing that is because the document itself is immutable. Only the topic assignments change at each pass. So therefore, if we split it into two different files, we only have to write one file. So that doubles our write speed when it goes back to disk. It also means that we can keep two copies around and not worry that much about it. Okay, so we open those two files, we read it in. Here we assemble topic assignments with the documents. As the internal data type, we actually use threading building blocks, but don't worry about that part. And then, depending on how many cores you have, each core grabs a document and resamples the topics in that document. So if you recall from the previous slides, right? This part here is local. So we don't have to worry that much about it. But each core gets one of these. And here's another trick that we use. The samplers themselves do not have write permission. They only read. We have a separate thread to write. Now why is this good? Because it's actually computationally a lot more costly to do the sampling and update the sufficient statistics. Because for the sampling, well, we still need to normalize and do all sorts of other things. Now that means that most of the code here doesn't actually need write permission. So we have much less code that needs to acquire a write lock. Write locks are exclusive. Read locks, you can have many of them. So that just makes the design in terms of locks a lot easier. You could parallelize that, but turns out that at least with 16 or 32 cores you don't need it yet. And then you have some other filter which just looks at whether things are going okay, and then it dumps it to disk again. So this way you can stream all of the data through. You only update the document that you're currently interested in, and in the end you throw everything back to disk. So that's single machine. And there is no limit on the amount of data that you can go through. Now if you look at Walpole Wabbit, it does something very similar, except that it doesn't use a sampler, but here it uses a basically a variational method. And it has to solve actually a fair amount of computation here before you can do an update. That's okay if you have a tiny number of topics, like 100 or so. As soon as you go to 1,000 topics, that will not work very well. Yep?
So in that diagram, only one of the samplers writes at any given time?
No, the samplers can only read. They create an update message. And this one has write permission. So that type of template, when you have most of the computation in a way that only requires reads. And then a separate thread, which does all the writing, we've seen actually being very, very effective. Okay.
Yep, just to clarify, so the things that the samplers are sending, the messages that they're sending the count updater, those are the word topic
Correct.
counts?
Correct. So essentially what they do is they send something like, this word has changed from topic 5 to topic 7. So that's more or less the updates that they are sending. Then the updater does some pre-aggregation, then it dumps it to memory. And it can be clever about, whether it actually needs to acquire a lock for the write or not. Because what can actually happen is, so we do clever reordering of, verb topic combinations by frequency of occurrence. And then in that sparse vector, when no new topic is generated or the order of topics doesn't change, you can actually just write the integer without acquiring a lock. So we can be fairly ruthless in that sense. So there's a lot of really clever low-level engineering that goes into that part. Now, how do you actually synchronize this? So you could have something like a distributed key value storage, and we'll look at the more general abstract version of that in a moment. But basically, you have all those samplers, those machines, that communicate with, well, Internet Communications Engine, so there's basically a remote procedure call library by a company called CRC. So that's really what happens. So that's also distributed. And we'll get through that in a moment. And then essentially we just update individual words, basically all the topic counts between machines. We'll get to that in a moment. So there's a whole bunch of other tricks on how to really make it work. So initially you could either randomly initialize the topics, or you can use sequential Monte Carlo. So it basically means that you almost have like an online procedure to initialize things such that it's reasonable. And the obvious thing is you want to have failover, like if you lose the data, well, you basically keep 2 copies. The only thing is if you lose a machine, you need to restart from that point. You can actually extend it quite a bit, so you can basically have a much better language model. So right now what I showed you is extremely primitive. It's basically just, a bag of words. We all know that this is wrong, so you can actually have, bigrams, trigrams where words depend on each other. You can condition on a lot of side information. You can condition on the fact that for instance in WordNet that certain words are similar. And you can make everything time dependent. So there's a lot of stuff that you can do beyond the simple LBA model. Now, I won't have time to go much into alternatives for inference. I mean, it's in the slides and they'll be up online. Because while this is really interesting, and I'm going to, some of my computers decide to save things now. Good. So let me just show you a summary of what I'm going to skip over. And that's effectively really the only part of the table that you need to know. So there are various techniques how you can actually try to tackle those inference problems. And so what you could do is you could, just use the uncollapsed, likelihood, and you could optimize over everything. So you could say, we have the topic distributions, we have the word distributions, and we have the topic assignments, and we just jointly optimize over everything. And if you do that, it overfits like crazy, because the mode of the joint likelihood is not a very good model for joint distribution. You can use a variational approximation that's actually fairly efficient, and that's like what essentially Blying and Jordan started with. The issue is only that this has a huge memory footprint, so you can pretty much forget about it. You can collapse the natural parameters and you still get parabol overfitting, and it's a really ugly discrete non-convex optimization problem. Or you can collapse the topic assignments, and well, it's still quite nasty. So what I would therefore argue is you actually use sampling. If you have everything uncollapsed, it doesn't mix very fast. Variational approximation and sampling don't really make so much sense together. But what you get here is that you get very fast mixing if you integrate out a lot of variables, so just like what I showed you. The approximate inference is still reasonably well understood. What's really an interesting frontier of how to push things further is basically how can we parallelize sequential Monte Carlo. And that sounds like a weird thing, how do you parallelize sequential Monte Carlo? So in other words, particle filtering, after all, everybody knows, you just spread the particles over several machines. Well, not really, because moving the state between different machines around is going to be more work than actually doing the sampling. So at the moment, this is an entirely unsolved problem. Now, what I'm going to do is take a step back and look overall at parallel inference as in, how can we solve large-scale latent variable models. So one thing I'm going to do today is, given that we lost quite a bit of time initially, I'm not going to take a break now, and we'll just keep on going until 7. Does anybody need a break in between? Okay, good. So, fine. So, here's what we have. So we have, well, this is basically clustering, right? So our data, cluster ID, it's like mean and variance, and then probabilities of those clusters. And what we effectively have is we have some global data, some global state, and every machine needs to know about that. I have some data which I have plenty of, which usually doesn't fit into my memory. Then I have some local state. And that local state is, possibly also quite a lot, but I don't really need to know it on the other machines. So that's what we have. It's way too big for a single machine. This is monstrous, and that you only care about locally. The same problem occurs in LDA. It's just plain vanilla LDA. So my global state here is basically the topic distribution for the documents. The local state is just the specific topic assignments. The data, of course, is the global evidence, of which I have plenty of. So that's basically like user activity logs, documents, whatever I have. And the global state, again, there is the word distribution for a topic. And you can do fancier things like temporal user profiling. So this is close to what we do if you come and visit Yahoo and want to find out what you're up to. You basically take that LDA model and you make it overall time dependent and moving over time. So in other words, these are the three problems. The local state doesn't really fit into memory. Well, you fix it by streaming it from disk. No big drama. The global state can be actually too large, and you have all those network load issues and lots of barriers. You can work through that by essentially synchronizing asynchronously. And then, if the things don't fit into memory, you only load the part that you really care about. So those are, in a way, the tricks that you can use how to spread out large-scale latent variable models. So, what it really means in practice is this. Yep.
So just, what do you mean again about partial view?
So it means, for instance, suppose I had English and Spanish documents, then you will have, an overall word distribution, and the machine that holds the English documents doesn't need to know the Spanish vocabulary. So you only really pull out the statistics that you care about, and you can do that by being clever about storing parts of the information on some machines. Or, for instance, suppose you're a social network and you want to, recommend content, then the machine that recommends your content doesn't need to know my preferences. So I only pull out, your preferences on the machine where you just ended up with, and then if you interact with that machine several times, that's probably kept in cache. So there are designs that are like that are in use in some networks. You can't necessarily do that for spam filtering, for instance, because you would cause a massive delay. In spam filtering, if you at least have to pull things from disk, you have a hit of a latency of 1 millisecond. But if you have a user showing up at your social network, and he interacts with that server for a couple of minutes, then you might have an initial delay of a millisecond, but then afterwards you're going to serve a lot of requests for that user anyway, so you don't care. Yep.
Are any of those sort of approximations in that usually this won't need that, so you only usually get that, but there'll be very rare cases when it does, and then it won't work so well, but maybe it doesn't happen often. Is that?
Sorry, I'm not sure I fully understand. Let me try to rephrase your question. Basically, whether there are cases where some things don't work, and
or whether are those heuristics, like as in partial view, for example, are there cases when you actually do need some data that you don't give it?
So the thing is, if you have a model which requires some variables and you just don't have access to them, then yeah, you're screwed. Now, there are cases where, so for instance, if you want to do social network factorization, where actually your state is really, really huge, and you need to make sure then you basically need to do fairly hard work to figure out how you partition your problem onto several machines, so that each machine actually has enough memory to hold the data that it needs to operate with. And that then gives you interesting graph partitioning problems in the first place. So there is a lot more work at the moment going on in that context. And yeah, so basically this is right now still very much under development. So for topic models and similar stuff, I think we have a pretty good idea. For social network factorization, not really. Okay, so here's what happens. I mean, and in some cases, well, you know, you have enough memory anyway. So that depends then a little bit on the company that's actually operating the hardware. You know, depending. So, you know, some companies have maybe some machines with a lot of memory. Some companies have a lot of machines with a very modest amount of memory, and then you need to change your algorithm. So it really depends on, let's say, whether you work with Microsoft, Google, Facebook, Twitter, or whoever. They might have a very different hardware setup. That drives your algorithm development quite massively, actually. So to give you an example, let's have a look at what happens here. So basically what we do is we make a replica per processor or per machine of the variables that we need. So that's really what happens here, right? So you basically have the global variable, you make local replicas. And that actually creates a hotspot if you do it naively in this way. Because this machine that has the global variable has to talk to all these machines that need a copy of it. So if you have a network setup that looks like so, where you have, you know, a switch on top of a rack, then you have another switch on top, you know, that ties all the racks together, then this would cause, you know, a heavy bottleneck up here, which you basically have a massive amount of oversubscription. So this round trip is expensive, whereas this one is still reasonably cheap. So what you then do is you make copies of copies. And in some networks, so some companies have a network setup that looks like so. And then you need to do those tricks. Some other companies don't have networks that look like so, but they look much more flat. I cannot tell on the record exactly who has that, but there are, for instance, nice papers out of Microsoft which describe how you can have networks that essentially look homogeneous. They don't look like, you know, racks tied together with the top of a rack and then another switch. So their network design looks a lot more like a modern phone network. So basically how you would have switchboards. Now, how do you actually do synchronization in this case? So I just said, oh, no, we have local samples and then we just tie the variables together. Right? So here's what we have. So each machine happily goes on, adds samples. You start with some common state, and then, you know, each child keeps a copy of, you know, what the old consensus state was, keeps on moving along. And then each child goes and sends, you know, copies of the differences from local to global. So this is my global state keeper, and we'll deal with that hotspot issue in a moment. So bear with me on that. Basically, all I'm doing is locally I'm just checking, okay, what was my old state, what's my current state, and I take the difference in the counts, and that's what I send to global. So for instance, if, you know, some topic lost some counts, well, I send that change. And then I track how much, you know, I basically say, well, now that I've transmitted that, I update my old variable. Global does nothing else but just says, okay, well, this is the change from machine number 5. Let's incorporate it. So that is a very simple procedure. The reason why we are transmitting diffs here is because the local changes tend to be smaller than the size of the global state. So what you need, therefore, is, you know, variables that admit taking differences. So basically, you need an inverse element here. So that requires a group structure at least. Now, what you, in addition to that, need is that the order in which those updates are incorporated doesn't really matter, otherwise you get really horrible scheduling issues. And that actually then requires that you get an abelian group. So anything that fits into an abelian group can be done with this. So those count statistics that I showed you are just a simple case. Now from global to local, things are actually very similar. What I do is I send my global state, now I send the entire state, and locally you just compare what your idea of that global state was, you compare it to what you've received, and you track and update. Yep.
Wait, so you're transmitting the entire global state?
I'm transmitting the entire global state for a subset of variables. And that is smaller than, let's say, this machine needs to find out what everybody else did. So you transmit the aggregate. And that is considerably smaller than, each message from the other children. So that's actually quite a bit more effective.
But it's not like the difference between the global and the...
Well, for that, otherwise, so as a matter of fact, that's what we initially did. And the problem is that if you did this, your global state keeper would need to know what locally was going on. In doing this, global doesn't need to know what the local machine is doing. For all I know, it could have crashed and recovered. So this is actually quite a bit more convenient. You could make this into a symmetric protocol if you wanted to. We don't do that because it's much more efficient to really keep things asymmetric, because then you have to send shorter messages upstream. Okay. So this looks really good, except that, well, you can do something really dumb. This is what we initially did. Or you do you basically use a remote procedure call library. So, but that's really technical details that I'm not going to go into right now. So, if you read the paper that we wrote in 2010, you will see a really stupid protocol. Okay. Now, here's something that you may recall from the beginning of the class. So, the thing is, you actually pick different machines to be the state keeper for those variables. So, let's say for the word house, the purple machine holds it. For the token machine learning, the red machine holds it, and so on. You pick a different random tree for each key. And you decide which machine is going to be the master by, just doing this argument hash. This way you get a uniform distribution of keys over machines. So in other words, each machine, is the master controller for a small subset of variables. And those subsets are of approximately the same size. Okay, so this is good, because now, well, storage is like 1 over number of machines. So the storage overhead for the global part is really small. Communications cost is order 1, because I have that 1 over k part. And I need to talk to k machines, so 1 over k times k is 1. That's good. And I can do very fast snapshots, because I only have a very small part of the global state. And yeah, you get this nice complete graph. So here's the problem. So if you have a lot of open connections, a lot of open network connections per machine, and you're sending data through all those connections, then stuff is going to slow down a lot. Because basically the amount of data that's exchanged between any pair of machines really goes to 0. And through that you pay a big overhead just for opening and closing network connections. So here's how we fix that. Basically, we pick a random subset of machines at each time to talk to. So who's done a bit of information theory? Okay. You may have encountered random codes. This is effectively what we're doing here. Okay. So here's what happens. Each machine picks some random machine it talks to. Okay. And now, well, okay, if we just pick one, and then once it's done with that machine, it picks the next one, another random machine, it keeps on going. It's not quite random, it actually picks a permutation to make sure we talk to all the machines, but what this does is it effectively means that we have a bipartite graph, except that at the global end, there are some machines that are being left out. So in this case, you can see that this machine didn't get anything, and this machine got 2 connections. Now, how do you fix that? You basically have each machine talk to maybe 2 machines at a time. And then, that load distribution here looks a little bit less horrible. I mean, you still leave one out, but, happens more rarely. And it actually turns out you can compute an upper and a lower bound on the communication efficiency of that scheme very easily. Okay. Let's just derive that for a moment. So, what we do is, we pick a random subset of machines. Now, picking a random subset is basically similar to what you do in a bootstrap sample where you draw with replacement. And you can show that the number of machines that don't even receive a single connection goes like e to the minus number of connections that are open. You can see that very easily by the following reason. So the probability that a machine does not receive a connection is, well, the probability that it receives a connection is 1 over n. So the probability that it doesn't is 1 minus 1 over n, right? Now I'm making n connections, right? So this is approximately 1 over n. Now if I don't only draw 1 connection, but d connections, then this becomes e to the minus d. It's actually slightly better than that because I make sure that all those d connections are distinct, but this will then give me a lower bound anyway. Now, therefore, I know that my communication efficiency cannot be better than the number of the fraction of machines that never receive any connection. Right? Because if I don't have any connection, I cannot receive any data, so therefore there can be no efficiency in that end. Secondly, I can compute the lower bound. The lower bound goes as follows. I say each local machine spreads its data load uniformly over all the machines that receive something. So if I have 3 connections, then each edge can carry 1/3 of the weight. Now at the receiving end, what I do is I say, well, if I have, more than 3 connections, let's say, then okay, that's just, it's not going to benefit me any further. If I have less than 3 connections, I will pay a small penalty. And so you can do the same Poisson reasoning. So here you can see what happens. That's basically the amount of data that I'm not getting. That's what I get from my Poisson approximation. And then if you just work that out and just hack it into Python, you'll see that about 4 machines or so are good enough to basically get a very good load balancing. So the bottom line is that through that I actually get a very efficient communications graph by picking 4 or 5 random connections at a time, and whenever I'm done with one machine I pick another random machine. Now this is very complicated wording for saying I pick a random permutation, and what it really does is it uses cryptography. Okay. So here's how cryptography and random permutations match up. Let's say I have a 10-bit message. Okay. So that, of course, means it maps to 2 to the 10 to 1,024 different objects. Now what I can do is I can encrypt this. And this is again a 10-bit message. So the encryption algorithms that don't make the message any longer. Okay. So now I have, that's also essentially in a set between 1 and 1024. Now, since it's an encryption, I need to be able to decrypt that again. Afterwards, otherwise it would be a hash, but not an encryption. So in other words, I have a mapping from the numbers between 1 and 1024 to the numbers between 1 and 1024, which is basically as random as can be. And if I don't like that particular mapping, I just go and use another key for the encryption. And that's how you get a random permutation for G. So that's basically how you can, get those permutations. To give you a bit of an idea how well it actually works. So what we did here is we varied the number of, in that case, documents, and up here is 2 billion documents, not million, billion. Right. It's 1,000 machines. That's basically one cube sampler sweep through a fairly large chunk of the user base. And what we can see is that as we, so the red line is basically you keep the number of machines fixed and you just throw more data at it. And the algorithm is essentially linear. But what happens is that usually as you get more users, you get more money to buy more machines, to throw more machines at the problem. Right? And okay, it doesn't quite exactly stay constant. And I think this is really where things start getting really weird with the network. But basically, things don't increase too much as you get more data. And so this is how you can do very, very highly scalable latent variable models at basic industrial settings. So to summarize a little bit, here's what we do. We have, some global shared variables, and we just make local copies. And we do all the local bookkeeping, and this is actually an approximation. The good thing is we don't really need any logs in doing so. The second thing is we, do asymmetric message passing. So, we send global state to local, and we send the diff back to global. And the third thing is, we do out-of-core storage. So in other words, we don't really try to load all the data into memory. Big hint, do not load each movie all into memory unless you have a decent data structure. It should not require a lot of storage, because if you have 10 million entries, right? And so what you need is basically 2 ints for the movie, for the user, and then for the rating. And then you have maybe a bit of payload, right? So we're talking about maybe 16 bytes. So 10 million by 16 bytes should not require more than maybe 160 megabytes of storage. If your code runs out of memory in trying to load that into memory, it's basically not very well engineered. And you're very wasteful with auxiliary data structures. Nonetheless, you can just stream it from disk if you want. So for Netflix, you definitely couldn't load that in memory a couple of years ago. Now it's probably a good time to have a short break for questions, and then we can look at advanced modeling, what other things you could do, for instance, instead of double models.